Hello, welcome to the Embedded Systems and Microcontroller Internal Assessment 1 answer key discussion. So let us see the question. Before that, I would like to say that there were two sets of questions given, set 1 and set 2. So there are some differences in terms of options in these two sets. Let me show both the sets and then discuss the answer keys one after the other. This is question set 1. I will be sharing this with you. When we correct your answer books also, we will mention it at the top whether it is set 1 or set 2 so that you will be able to verify the answer. So the first question is, register inside a CPU that points at the address of the instruction that it has to execute next. It's very obvious. It's a program counter. What are the other registers? Stack pointer, which points to the top of the stack currently, and the instruction register is the one which stores the opcodes that have been read from the code area. So program counter is the one which holds the address of the code that the CPU is currently executing or going to execute, because it's going to fetch that instruction from the memory which is part of the code and going to bring that instruction into the IR instruction register and then it will execute. So the answer for this is C here. In the set 2, the option is given as A, so you need to be aware of this. Now what about the second question? Walkme is a web-based online simulator for electronics and embedded enthusiasts. So since I have mentioned the electronics and embedded here, both simulator and emulator work well for this option. So we will consider both the answers as correct one, and A and B in the question set 1 are the answers, and in the set 2, A and D are the correct options. Now coming to the correct sequence of various phases of software program development, which is very obvious. We first edit the program, and then when we say compile, the preprocessor comes up first. It handles the hash include, hash defines, if def, or any macros that you have in the program, and it expands them and prepares the code for the compiler to work on. So the preprocessor is the first tool to look into the code, and if there are hash include, it opens up the SDTO, IOH, or whatever include files you have put at the top of the C program, and then the compiler looks at the holistic view of the file, which includes the header file as well as the code that you have written. So preprocessor comes after the editing when you are compiling. Then you actually the compiler starts converting the code into assembly program. Suppose you are compiling it for an Intel processor, then Intel assembly code is generated. If you are compiling it for an ARM processor, like what we do in RP2040 on Arduino IDE, it generates a ARM assembly. So which is finally be a .obj file, or we could be developing a link library file, then it would be a library. But both will have the object code in a binary form, or the assembly instructions in binary form. Then we bring the built-in library CLib or any other library which implements the basic C functions like malloc or printf or scanf. So linker puts in all the library files as well as your own obj files, which can be one or many, and then generates an executable. Now once the executable is ready, either it should be loaded onto the main memory of the laptop or a PC for it to be executed, or if it is a case of RP2040 or Arduino or any board, then that executable has to be loaded onto the board, which we call it as upload into the board. So we load it and then we execute it. So this is the sequence of operations that we do for a software development. Now C is the right option. if it is a set 2. Now let us go to the fourth question. Access permissions to the memory area allocated for the code area of a program. So you know that a program has many areas which are accessed while the program is being executed. Code is the one which is having the instructions and that are in binary form, the assembly instructions, which is first accessed, and based on the instruction being executed by the CPU, we may be doing a load or a store operation on our data, which will be part of the data area of the program. And then if it is a local variable, it will be using the stack area of the memory. So there are basically data, code and stack area each program that you are planning to run will have. So what are the access permissions? Actually, this whatever is given is with respect to the operating system. Since you are not very familiar with operating system right now, we thought that we will also give read only also as a correct option. Actually speaking, from the OS perspective, it's a read and execute. That means the code area of the program is not only readable, it should also be having an execute permission, because you cannot arbitrarily read any part of the memory and start executing it, because it should have valid opcodes into that memory area. So with respect to the OS, it should have been read and execute, but since you are not familiar with OS, you might be thinking that only read or write operation that could be performed on the memory. So we are going to give you both A and D as the right option. In the set 2, it is A and C. Okay. I hope if you are given any of these answers, you would be getting 1 mark here. Now, let us go to the fifth question. The behavior of a software running on a CPU accessing the data or code from the nearby addresses. See, the word nearby means that the addresses which are closer to each other. It could be a data access because it's executing a program or a function, uh, or it could be an array of elements. So if it is a data access, it will be an array of elements. If it is a code access, it will be maybe a function or a for loop where nearby instructions are going to be accessed, and the CPU will be executing them. So that kind of a behavior in software is called spatial locality of reference, because it depends on the space or the memory locations which are nearby are being accessed. Either it could be data or a code while a program is being run. So temporal locality is not a right option, because that refers to the timing. In terms of time, if it was accessed very recently, it is most likely to be accessed in the future too. So here I am referring to the nearby addresses and not in terms of time. So temporal equality is not the right option. Data memory referencing, it doesn't make sense here, because the nearby addresses could also be code. So B is also not the right option. Spatial locality of reference is the right one. Now what about the set 2? B is a special, spatial locality of reference. So 5 questions are done. Now what about the sixth one? The memory type which is constructed with just one transistor and a capacitor. I hope this we have explained it. The construction of DRAM, which is memory used for main memory especially, and which needs to be refreshed very often, because the capacitor has a tendency of losing the charges over time. So we need to recharge them frequently. But we use DRAM for main memory because it occupies less space, so we can pack more bits into a given area. So this is also made of a semiconductor which has a one transistor which is like a switch, and a capacitor which holds a charge. So DRAM is the right option. ROM and SRAMs are different, and SRAM is constructed using many transistors. It occupies more space, it consumes more power, and that is used for cache memories, but not for the main memory, and it also consumes more power compared to DRAM. And ROM, you know, that read-only memory, which is not constructed using one transistor or a capacitor. It is the construction is totally different. So the right option is DRAM. And set 2 has DRAM in as a option, so that's the right answer. Now let us go to set 1. a CPU with three levels of caching. So when I say three levels, it is L1, L2, L3 from the CPU. So L1 is very close to the CPU and the L3 is farther away from it and main memory is still down. Now, when the CPU is accessing either code or data, that could be an instruction cache, data cache, or unified cache, wherein both code and data reside, it needs whatever code or data it needs for execution. What is the level which the CPU is going to access it more often or with a higher probability? The reason that L1 cache is the right option because once the data or a code which the CPU is executing currently is moved into L1 cache, because of the spatial locality or temporal locality of reference, I told you that the program will be executing around the given area or it will be accessing the instruction which it has accessed very frequently. So those instructions are already available in L1 cache. So the CPU will be more frequently accessing L1 cache than the other caches. Hit will be more, miss will be less for L1 cache and the probability will be more for accessing the L1 cache. So A is the right option. Here L1 cache is appearing as a B option in set 2. Now let us look at the multiple levels of memories and their properties. Now T is access time. That means how much time does the CPU take to access a particular level of memory. It could be I is a level which is closer to the CPU and I plus 1 is the one which is farther away from the CPU. So you know that access time is lower if the level is closer to the CPU. That means Ti will be lower than Ti plus 1. Okay. Now what about memory size? I told you it's a pyramid kind of a structure. L1, L2, L3, they increase in size as they go away from the CPU. So the size of memory at level I will be smaller than one which is at I plus 1. So Si is lower than Si plus 1 is also the correct option, right? Then what about the frequency of access? I told you in the previous question, L1 is going to be accessed more often. That means frequency of a level which is closer to the CPU is going to be more than the one which is away from it. So the option D is the right option for the question 8 in set 1 and it happens to be C in the case of set 2. Now let us come to the library function which is part of the Arduino IDE. I'm sure this program you have read it, did in lab. We try to read a character which is being printed or sorry, typed by the user from the serial monitor. You are checking whether it is a character has come from the laptop to the board. So the library function which returns the total number of bytes or characters received by the board through the serial port is serial available. So you can choose the option based on elimination method also. Parseint is actually parsing the value, whatever number you have entered, it is going to return the integer equivalent or decimal equivalent of that value, which is not the right option anyway. Serial begin, you know very well that it is for setting up the baud rate of a serial protocol between the laptop and the board. And serial println, which you are very much aware that it is for printing the error messages or whatever message you want it to be seen on the serial monitor. So none of these options are correct and serial available is the one which returns the number of bytes received. So A is the right option here and B is the right option in the set 2. So let us look at the 10th question. Now this is what is an interesting question which takes little bit of time to solve it. So let us spend some time here. Now let me show you. Okay, let us see question 10 now. It is given as a signed int, and the value in k int happens to be minus 8. Now, the first thing what you need to do is to find out the binary representation of this value minus 8. Now, how do we find out? Very simple. First, find the binary representation of 8, which you are all aware is 1 0 0 0. Now, since all the values in the RP2040 are 32-bit wide, so this is going to have the 32-bit quantity, which is like this, and 8 is this. Now what we need is a minus 8 and its equivalent representation of binary in binary form, which is a 2's complement of this value, whatever the magnitude is. So you have to find the 2's complement now, which is all ones starting from bit 31, and then this particular bit whatever we have will be 0 and followed by 3 ones. So this is bit 0, right? Now we need to add plus 1 to it, which will be again 1 0 0 0 all ones. So the value will be all ones followed by 3 zeros. So this can be represented as FFF. This corresponds to 16 bits, and then F, F8. This corresponds to the last nibble, and there are 4 into 8, 32 bits. Now this is the value which is in k int. Now this is going to be right shifted by 2 bits, and this happens to be a signed integer. Remember, it's a signed integer, sint, but or signed int. So we need to take care of when you are right shifting it. It's a arithmetic shift what we do. So the once what is there, the sign bit which is there in the MSB part will be moving in. So we will be making it as FFF only. Now when this whole bit pattern moves, these two zeros will go out of the register, and it will end with 1 0 here, right? So it is 1 0 here and then all ones here, which happens to be this value. Last 4 bits, if you see, it is 110, which is E. So if you write it in hexadecimal form, it will be F F F F F. This is also F, and the last element will be E. So how many F's we write? Each F is for 4 bits. So we will be having this value after this k int is right shifted by 2 bits. So we want to do a XOR operation. This is XOR operation, which you are all aware. XOR operation is done on this 32 bit with a value which is 0xFF. Now when we are doing XOR operation, we need to make sure that the higher order bits are also taken care of, because it is a 32-bit operation which happens, whereas what you are loading is only FF, that 8 bits. So let me write the value that we have already, which is this one, and what we are doing is we are XORing it with these are all zeros, and this is FF FF. If you convert this into decimal, this portion is very clear. Okay, up to this, these are all zeros and these are all ones. So when you XOR it, it will be resulting in ones. So up to this, you will have FF up to this point we will have f. Okay, so because all it will become, this is, if I write it in a binary form, 1f and then on 0 here, this 0 and 1 results in 1 XOR XOR, so these are all 1. So you will get how many f's? There are 6 f's you will get first. F, 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 then there is 6 f's you get. Now what about this last two values? That is, f is there. The two things are f here. This is also f, this is also f. So it is 1 1. So that will be 0. This whole nibble will become 0 because you have both are having ones there. Now what about e? Now let us look at the lowermost nibble that you have, which is in the top. It is e, which is 1 1, 3 ones followed by 0, and f is 1 1 1 1. So these three bits are same, both are 1 here. So that will result in three zeros because we are doing XOR operation, if you recall. And the last LS bit will be a 1 because it is different. So what you have will be this value, 6f followed by 0 1, which happens to be the option A in set number 1, and it happens to be here in set number 2. C is the right option. So to summarize the part A answers, the table what you should have filled in should have these values. Okay, we are giving both A or B as the right option and A and B here. Whereas for the set 2 question, what you fill in the table should be this. I hope this is clear. Now let us go into part B. Now here also there happens to be a surprise. Question 11 and 13 are interchanged in the two sets. So let me show you. If you see this binary pattern of 1 0 1 0 1 1 is question 11 here, whereas that happens to be question 13 here. So this these two are interchanged, and the rest of the questions are in the same place as both the sets. Okay, so now let us look at question the set 1. Okay, whatever we do here will be valid for question 13 in set 2. Okay, so let us look at what are we supposed to do here. We have a int which happens to be an unsigned integer. We are performing the following operation, which is having initially this value. Now let me write a int has a value which is 0x, 4x followed by 4 zeros. Now we need to right shift it by 4 bits, and remember this happens to be an unsigned integer. Okay, though it's called a int, the variable name, you have to see the declaration. It's an unsigned int, which happens that when we right shift, we will be moving in zeros into the value. So since it is rotated by it's right shifted by 4 bits, we can see that the 4 f's will be moving, and what you will have is in hexadecimal form, 0 will be there, 4 zeros equivalent to 1 0 here, then we have this, and then 1 f has come here, then there are 3 zeros only because 1 hexadecimal 0 is equivalent to 4 bits of binary values of zeros which go out because of this right shift operation, which is shown here as right shift by 4. Now what are we doing on this? We are going to do an AND operation with the value AA55. So AA55, and then if the higher values are not given, you can assume it to be zeros. Now this is in hexadecimal form. We want to AND it, bitwise AND, which is just an ampersand symbol. So when you are ANDing this, you know that both ones should be resulting into 1. So this whole thing will become all zeros. So the higher value, whatever is here, will become 0. So let us fill it up. AND operation is going to result in this 16 bits, 4 into 4 are going to be zeros. Now what about this F and A? If I expand that F, you know that it is all 1, and this is A, which is a value 10, which is 1010. So if you AND it, it is going to give you 1010. So this will be A. This will result in A. What about this? This rest of the bits are 0 here. So whatever value here, whatever pattern you have here, doesn't matter because the top one is all zeros. So this will result in 3 into 4, 12 bits being 0. So the answer is 0x. You can write it as 8000 because leading zeros here doesn't matter if whether you want to mention it or not. So the correct answer is this. Now I want to go into this other C operators question before we solve other questions. So this is set 1 in question 13. I am going to look at it here, what is being shown here. Whereas set 2, it is shown as question 11. Okay. So now let us see what is being done. Here also it's unsigned int, but only difference is this A int is getting initialized with a binary value. See, you know that 0b means binary value, which is 1010 and 111, which is nothing but A in hexadecimal, and F is there. Then the rest of it values are 0. So you need to always consider it to be a 32-bit value. So fill it up like this. So A int is having this AF as a value. Do not forget the leading zeros here. Now what about this A int which is getting OR? Here we are doing a OR operation with FFF. So let us see what happens. When I OR it with FFFF, 4 F's, I need to write FF here, and then it means that the higher values are all zeros. When I do a OR operation on this, you know that any one is 1, then the result will be 1. So we will have FFF as the output. Whereas here all of them are zeros, so you will have 4 zeros here. So this is the OR operation which is getting done here. Then we are going to perform an AND operation. Please remember, when parentheses are there, what is inside the parentheses is operated upon, because it's as a higher precedence, and it will first evaluate what is inside the parenthesis. Similarly here, before performing the AND operation, both the values which are within the parentheses are evaluated, and then the AND operation is done. You should not do AND operation here separately, because we cannot do it unless you have two values to perform an AND operation. So you need to compute the values what are there within the parenthesis. So now we need to find out the complement of this 0xF. Now when you want to find a complement, a ones complement of a value which is 0xF, again a simple logic is write it out in hexadecimal, of course. And I want to complement it. Now when you complement this, all the zeros will become 1, of course. So what will happen is this all will become F, and the last two nibble will become 0. So that is the value which we are going to AND it with the one which we got earlier. So this is going to be, and we are going to perform an AND operation between these two values, because this is what we got after the OR operation, and we are going to perform an AND of this. Now let me rewrite the value which is there above. This is all zeros, and we have F, F, F and F. Now what is this going to be? Very simple. We are performing an AND operation here. So this will become, of course, 0. This is, or both are 1. So this will be F, F. Here one of them is 0. So this will all be 0. So the final answer is 0x FF, leaving out the zeros which are not to be considered. This is the correct answer. So we have solved 11 and 13 on set 1, which happens to be 13 and 11 on set 2. Okay. So I have given the solution here in detail. The 11, I told you that 8000, and here it is FF00, which is what we got here, FF00, and 8000 we got it here, the previous question 8000. Okay, this is 8000 is here, and FF00 is here. So what we plan to do is, this is how we want to distribute the marks. Partial marks will be given if you compute at least one of this what is within the parenthesis correct, or even if you do a complement of this value, you will be given 0.5 marks. So we will see the steps, and then accordingly we will give you the marks. So here again 1 mark for performing this right operation, and then finding out the correct answer at the end, we will get a full 2 marks. Okay, so this is about 11 and 12, sorry, 11 and 13. Now what about this, the description? Now question 12 asks you to find out whether RP2040 falls under what category it falls under in Flint's taxonomy, and justify it in a few words. So we don't expect you to write lot of stories, because space given is also less. This much is enough. You need to know how to bring out the most important thing that you need to write in the given area. So RP2040 falls under MIMD architecture because it has dual cores. And why I am saying MIMD, it's because both the cores are accessing the instruction independent of the other one, and while they are accessing the instructions independently, they will also be accessing some data based on the program which is being run on each core. So they will be, each core is accessing its own data and its own instruction. Because there are two cores, it is a multiple instruction. Okay, whenever we say MIMD, remember it is for the entire chip RP2040. It's not only for Cortex M0. If I say only Cortex M0 plus, then it is a simple SISD architecture, because single instruction stream is coming and it is operating on it. But when I am talking about RP2040, we are talking about the dual core operate processor, and both the cores are running in parallel, and both of them are having their own program to execute on, and they will be having their own load and store instructions for accessing the data. So it is a MIMD architecture with respect to the RP2040. Now what about whether it is an SMP? SMP is a symmetric multiprocessor. That means both are identical cores. They run at the same speed, the same 133 MHz. So we call it as SMP because it's a symmetric multiprocessor, because they are identical cores executing at the same clock frequency, but they access different part of the instruction, and based on that instruction they execute, they will access different data. So it falls under MIMD SMP. So you have to say that which category it is, and then each core is connected to the bus fabric. Now The second question is, in the sub question is it a Harvard architecture or Von Neumann architecture? Now, this needs little bit of explanation, okay, which we have mentioned it in the class. If you are attentive in the class and you were present and listening to the class, then you should have got this answer. Now, what is why is it called Von Neumann and not Harvard? Now, let me explain now, even if you have missed the previous one. Core 0 is there, core 1 is there. Now, they are connected to bus fabric. As I mentioned, we have mentioned it in the class. They are connected to bus fabric, and these two are masters. Master port, maybe one master port, and there is another master port. That means they take a decision on how and what area of the memory to be accessed. So, the slave devices are SRAM or ROM or whatever, and they access it from the core. Now, so memory is below the bus fabric. It could be ROM, SRAM or ROM, and then the access is happening from the cores. So see here, both code flash is somewhere here outside the chip, and then it is accessing them. Flash is getting accessed from the external memory, external flash, and then it enters this through the bus fabric to the core. Code is accessed from the flash and comes in to the core, and the data is accessed from the SRAM, which is here, which is within the chip. Now, data is also either written into or read from. Now, if you see that there is only one physical interface connecting the cores with the bus fabric. So, if there is only one physical interface, both code and data has to travel through the same physical interface. That's why this is not a Harvard architecture wherein you have two different physical interfaces to the code and data memory. Whereas Von Neumann architecture, we have a single physical interface for code and data. Here, both flash memory, which is feeding in the code for the core, and the data SRAMs are connected to the bus fabric, and they need to go through this one single physical interface. That is the reason this falls under Von Neumann architecture. Okay, so if you have not mentioned one IMN, then there will be some marks will be reduced. Maybe we will decide how much it is. It's going to be maybe zero point 0.5 marks, and then we will give for MIMD architecture uh, 1 mark. We'll decide that and let you know. Okay, I have not put it here. Then what about this? We wanted you to expand this particular nomenclature, which I have explained, and we had a quiz also on that. How to find out this number correspond to what? So the first two which is there is number of cores are 2, and then the second 7 represents what Cortex M0 family processor is inside this chip. Suppose somebody builds their RP2724, if Raspberry comes with a chip like this, then inside of the chip these are the configurations. So M7 would have been the core which is inside, and then the second one 2 refers to the value which is the powers of 2, and then you need to logarithm to the base 2, and SRAM divided by 16k. If you calculate that, it would have been a 64 kilobyte is the size of SRAM this particular chip would have. And then in uh, our chip we have a lost value being 0, whereas here non-volatile memory is, suppose if they have built in within the chip, then it will not have a zero value, it will have a non-zero value, which happens to be 4 here. So which corresponds to 2 to the power 4 into 16k, because this is what is getting divided, so it will come out up there. So you will say that this is 256 kilobytes. See, please refer the relevant PDF or the slide that I have shared, and you will be having the correct answer. So each one of these answers will get you zero point 0.5 marks. So that summarizes the 14th question. Now fifth question, what is the program? It's very simple. We have a serial begin, setting a baud rate to 9600 and setting the GPIO pin 4. You have to mention GPIO pin, not the pin number, to output mode, and then we write high into that first and then wait for 500. So it will be on for 500 millisecond. Remember, this number inside the delay is in terms of millisecond, and then it will be low, it is made low, and then we are waiting for 1000. So the amount of time the LED is going to be off is for 1 second. So it's not at the same time, it's on for 500 millisecond and off for 1 second or 1000 millisecond. So explanation should be, it blinks the LED connected to the GPIO pin number. So you have to mention GPIO pin number. If you say just a pin number, which is wrong, at different rates for on, which is 500 millisecond, and off for 1 second. Note, reduce only 0.5 marks if on and off times are not given correctly. So we are going to reduce only 0.5 marks for this. So we will be evaluating it based on the key, and this summarizes the answer key for IA1. Hope you have done well. Bye bye.